Hello, after the pizzas. So, continuing on to Robert's lecture right now. And Robert will be talking about Apache Flink and all the problems that we described with working with databases and streaming frameworks, etc. And Robert will show us another solution to all of these streaming problems. So thank you very much for coming, Robert. And your stage.
Thanks a lot. Thanks a lot for the warm welcome. And I'm really, really excited to be here in Israel today for this entire week. So Eugene and I do a little tour of all the companies here. So if you're interested in talking to us, reach out to me or Eugene, who's sitting in the back. We're really happy to get in touch with you and learn about your Flink use cases, about your streaming problems. Because I have the feeling that there's a lot of stuff going on here with streaming in all kinds of use cases. And I've had already very interesting conversations in the last 2 days. So I'm hoping to continue that in the coming days. So in this talk, I would like to give you an introduction into Apache Flink, some of the core principles in Flink, some of the basic ideas, and also some implementation details. My primary goal for everybody who's here today is that you walk out of this door and you say, I learned something and I understand a little bit about Flink. So if this turns into a really interactive session, that's perfect. If you walk out and you learn something, let's make it interactive. Otherwise, I have slides prepared and we can also go over the slides. But feel free to interrupt me at any point in time. I think it's easier to discuss when we're at the slide about the specific details and then move on. So I think that's the setting that I like the most for a meetup talk. And to get started, I would like to know who heard about Apache Flink before this meetup. Perfect, that's really good. Basically everybody. And who has played around with Flink and did some POCs or use case? Very good, it's a good number. And who's running Flink in production? Perfect, awesome. So I would like to have all your names. Okay, so maybe, so my name is Robert. I'm a co-founder of Data Artisans. I'm also a committer and POC member of the Apache Flink project. We started this project more than in 2009, and it started as a university research project, and we turned it, we submitted it, we donated it to the Apache Software Foundation, and we also created this startup called Data Artisans in Berlin, in Germany, that supports the development of Apache Flink. And we've also launched, at the end of last year, we launched our first product called Data Artisans Platform. It's basically a layer on top of Apache Flink, making it easier to manage stateful streaming applications, and also comes with a supported version of Apache Flink. But this talk is going to be entirely about everything that's available in open source. So first, I'm going to very briefly talk a little bit about the history or definition of streaming. Then I'm giving Apache Flink 101 intro. Then I'm talking about production users and use cases. And then I'm talking about the 4 main ingredients of Flink that drive the use cases and that make Flink unique, and also the reason why Flink is so popular. Next, I'm going to talk about the APIs of Flink, so that you see how you can actually use all these powerful features. And if time permits, I'm also going to share some implementation highlights, like how certain features are implemented in Flink. And please let me know if you think that I can go faster or slower. Let's make it interactive. So stream processing emerged in the beginning as part of something called the Lambda architecture, when we had batch processors that were supposed to do the correct processing, like Hadoop or Spark, and you wanted to have faster results, you wanted to reduce your latency, and that's why you had one path where you did the batch processing, like every 8 hours or so, and then you had the fast path where you had a stream processor, usually it was Apache Storm, for getting fast results. But it wasn't supposed to be correct. The second wave of stream processing is analytics, basically replacing batch and making batch real time so that you're not waiting for your aggregations to update every 8 hours. Basically your aggregations are updated as the events arrive at the system. And also if you look at how data is produced, data is always produced in a continuous fashion. It's pretty artificial to say, let's collect events in a file and then process this file periodically. In reality, you have web servers, you have apps, you have IoT devices that are continuously producing data. So you want to also continuously process data. And I think that's the main idea of stream processing and streaming analytics. So it's actually a much more natural fit to analyzing data. Batch is probably just like a step in between. If we look at the grand scheme of things, if we read the history books about data processing in 20 years. But there's actually a much broader case for stream processing, and that is actually event-driven application. So it's much more than just having real-time aggregations. It's something where you react to input data immediately. It's something where you have your application logic or your business logic implemented in a stream processor. Like you're a bank and you want to send a notification to your customers based on a behavior. So it's more than just getting a number, it's really interaction with the user. So to understand how all this is possible, I would like to give you a brief introduction into Apache Flink. So it's an open source stream processing framework, and while implementing the system we focus on low latency, high throughput. We provide means for stateful stream processing. In my opinion, this is the main benefit and the main distinguishing feature of Flink, and it's a distributed system. So it scales with your workload, it scales by just adding more machines to the problem, basically. It's developed by a pretty large, vibrant community at Apache Software Foundation. It's more than just data artisans who's supporting Flink. It's, for example, Uber and Alibaba who are actively participating in the community. And Flink 1.4 is the latest release. It's widely used in production, and the Apache Flink website is basically the starting point for your Flink journey. It contains like a quick start, contains links to the mailing lists, which I would really recommend to use if you have any problem, because I think there's so many users in the mailing lists that have solved all these problems already, so it will be really easy to get some support. And the main use cases that Flink supports is batch processing. So Flink historically comes from a batch processing background. That's why we have an API called the dataset API. That's an abstraction for processing static files. That's comparable to Apache Spark, basically. But you can also use the streaming API of Flink for doing batch processing. There's really not a big problem to just let the streaming API read static files and then stream them through the topology. For stream processing, that's actually the main use case of Flink, like streaming analytics, and as I said, also event-driven applications. So really custom application logic using the low-level primitives of Flink for stateful applications. A little bit more technical. Basically, you have different data sources like applications, devices that are somehow generating events, and these events are either put into a stream using its Kafka or Kinesis, or you put them into static files for like historic data processing. And all these data sources, Flink can read from all these data sources and then produce data into all kinds of downstream systems. So I said in the first slide of the 101 section, who's using Flink in production? And Uber recently published a GitHub repository for their AthenaX platform, which is an in-house streaming SQL platform allowing their data scientists to access data streams using SQL. Netflix presented at our user conference, so we have a user conference in September in Berlin and in April in San Francisco. And at the last one in San Francisco, Netflix presented their streaming platform as a service. They're running more than 3,700 Docker images with Flink in production. It's mostly used for streaming ETL use cases, but they're also working on recommender systems, machine learning use cases with Flink. And they really have built also an internal platform for orchestrating and managing these jobs. Our biggest production user is probably Alibaba, the Amazon of China. If you look at their numbers, it's like business numbers, but also Flink streaming numbers. It's just crazy how many jobs, how much data, like over 1,000 nodes, terabytes of state. It's huge. They also provide now the internal Flink platform through Ali Cloud, the cloud offering. And Alibaba is also a huge collaborator on the open source community. So they are the main contributor behind the Steam SQL abstraction in Flink, and also in some of the deployment components. And a company from Europe, ING Bank from Holland, Amsterdam, they're using Flink for fraud detection, and they're also building an internal streaming platform to allow the developers to easily develop Flink streaming jobs and put them into production. So very briefly, Athena X at Uber is, as I said, publicly available on GitHub. The users can basically choose from a different set of data sources like Kafka, MySQL changelogs, and we talked about this, and also Cassandra changelogs, and they provide like a high-level interface for writing queries that are compiled into a Flink job and then executed on a Yarn cluster. And that's pretty interesting stuff because it allows people to do stream processing even if they are not able to write in Java or Scala or any other programming language. So it opens up stream processing to a much broader audience. And Uber is using this platform, for example, for demand forecasting. They're also using this for just tracking like how many active users they have in certain geolocations. So this is actually critical to Uber's business. Yeah.
Flink with a pipeline DB first. Does it provide similar functionality?
Pipeline DB?
Yeah.
Sorry, so the question was whether I can compare Flink with Pipeline DB, and I have to admit that I don't know Pipeline DB.
Okay, fair enough.
Yeah. But we can maybe talk offline and maybe we find out together the differences. Alibaba also has an internal streaming platform, and I'm just having this slide here to see what applications they are doing with Flink. So their search is powered by Flink, recommendation system, ad delivery, business intelligence, and security. Alibaba has a very interesting day once a year, which is Singles Day in China, which is like this very crazy shopping day where they reduce the prices by like 50% and they make like a crazy amount of revenue on this day. And for that day, the engineers are preparing for months to have the system ready for handling all the shopping events and all the recommendations and everything. It's a pretty crazy thing that they're doing. And the last company is maybe not very well known. Maybe you know these guys from Top Gear or Grand Tour on Amazon. So it's basically a social network for car enthusiasts. And the cool thing about this social network is that it has actually been built on top of Apache Flink. So the main state, the main ground truth basically of the social network is built on top of Flink. And the way it works is, whenever you perform an action on the website, let's say you like a post, or you join a group, or you retrieve the front page with your news stream, the last one is not computed by Flink, but it's computed by Flink, but whenever you perform an update, this update is written to a Kafka topic, and then Flink reads from this Kafka topic and computes, for example, the number of likes per message or the members per group. And then the result is written to Elasticsearch, and the front-end servers are just retrieving JSON from Elasticsearch serving the data. And the interesting thing is that they have like a blue-green deployment model. So they have two clusters reading the data from Kafka. And if they want to upgrade the version of their Flink job, they bring down the new version on one cluster, wait till it's running, and then it basically sends the data to the live system. Then they can bring down the old cluster. But if the upgrade fails, if this migration fails, they can basically roll back to the old version of it. So they can very easily, very dynamically manage the infrastructure using this red-blue deployment model. So to summarize the use cases in Flink, it's streaming analytics pipelines, as we saw from Netflix. It's machine learning and search, that's what Alibaba is doing. It's SQL, for example, Uber is doing, fraud detection. So ING is, I think, using TensorFlow, it's just calling a TensorFlow service to do fraud detection. And Tribe is this very special model of building a website using a stream processor. And also we are interestingly working with a lot of banks. It's both investment banking but also retail banking. And they're working on reporting for compliance purposes, but also just position keeping, like the ledger, and also balance sheets and risk assessments. So there's a fintech.
Is any of these code available to watch? I mean, for this company?
So the question is whether this trade processing is publicly available, and sadly it's not. I have some.
Any of the examples, the company.
We can talk privately about this, but since it's big banks and also customers, but I can show you some slides about more details on what they're doing. But it's
maybe like reference.
Yeah, but basically the underlying problem is that the requirements for reporting to government authorities get higher. Like they have to report much faster on their risks and their positions, and that's why these banks are looking into streaming technologies, because it doesn't help if you know your risk at the end of the day. You want to know your risk in real time. And that's the reason why these banks are really badly looking into these technologies. So let's dive a little bit deeper to look into the building blocks of Flink that actually enable and power these use cases. So there are 4 building blocks in Flink that are really important. Number 1 is event streams, the possibility to send data through a pipeline in real time through operators. State, which allows you to basically state is the move from having a web server that just serves static websites to having a web server that is able to understand who he's talking to and generate user-specific contents. And basically the same also applies to a stream processor like Flink, where Flink knows something about the history of the events, maybe something about the user, and then can derive better updates or better transformations on state, on the events. The next feature is event time, which means that Flink provides tooling in the framework for dealing with out-of-orderness. So it allows you to handle time in different ways. So whether you want to whether you want to just look at the system time when you're processing, or whether you want to take into account the time when the event has really occurred in reality. So that's another building block. And the last one is the snapshots in Flink, the ability to take a complete snapshot of your application state and migrate it somewhere else, upgrade it to a newer job version, upgrade it to a new Flink version, or just run the job in parallel to do A/B testing on your streaming job. So it's really powerful, and in particular for operations. So event streams are basically defined using Flink's APIs. So this is an example of Flink's Scala API. You see that we have this data stream abstraction. We have generics where you put the type of the events. From the environment, you define a source. In this case, we have a Kafka source. Then we have some simple transformations like a mapping where you're basically passing some JSON string into an event object, and then we keybind this stream by an attribute. So Flink, so if you're using a Pojo, plain or Java object, it knows which fields it has, and you can just specify the name of the field and then partition the stream based on the field name. And then we do something interesting, which is defining a time-based window. In this case, it's a window of 5 seconds. So it will collect data for 5 seconds and then perform an aggregation on that data. And how this time is understood depends on the configuration, whether you're using event time or processing time. And the result of this aggregation from this window is then written into the stats data stream, and this is written into rolling sync, which is creating files like every hour or so in a distributed file system. So this is basically how you express yourself using the Flink data stream API. If you then execute this, Flink will transform this into this logical representation of operators. So you have first the data source, then you have a transformation, this is map function here, then you have the window operator, and finally the sync. This window operator is performing state access. So the contents of this window, these 5 seconds of data, they are kept in Flink's state. And also the offsets of this Kafka source are kept in Flink's state. So if anything fails, Flink will be able to recover to the last stable checkpoint and then restart the processing from there. And it does this with exactly once semantics, which means that all the counters and all the elements in this window will be aligned. You will not have any duplicates. So how does the engine executes this on a distributed system? So you have this logical abstraction of the job, and what it will do as soon as you submit it to the cluster, it will turn it into like a parallel data flow. And you see here that there's a data exchange happening here. There's a shuffle because you're keying the stream by the sensor, and you need to basically assign all the data so that all the data from the same sensors ends up on the same machine, so that we can build the window here. The interesting part comes into play when we look a little bit about onto the state. So Flink has the state locally at each operator, which means that it allows you to scale the state very easily. You can scale basically the state with your application. You have memory speed access to state, and as I said, it scales. So let's have some data running through it. I also visualized here that actually the state influences these events usually, so you do some enrichment here or you do some counting or whatever based on the state. As I said, this state is backed up for you, so if anything goes wrong, Flink will be able to recover to the latest stable checkpoint. And this is happening through a checkpointing mechanism. So periodically, whenever I click these buttons here, Flink is creating a copy of all the operator states. So basically it sends barriers through the topology, and as soon as the barrier is at an operator, this operator will very briefly pause the processing and send its current state to a central distributed storage. And once all the operators have been have seen this checkpoint barrier, this checkpoint is considered complete. It's consistent because this barrier will never overtake any record. So it's always basically it always looks at the operators at the same point in time. No record can overtake this barrier. And the great thing about having the state checkpoint externally, and also it's addressable, so you can use this also for rolling back computation and also this A/B testing use case that I've mentioned. So you can reload the state back into the operators whenever you want. Yeah?
You said that the operator paused when the checkpoint, but isn't there a possibility to do this asynchronously?
Yeah. So the question was, they said that the operators pause when the checkpoint barrier is at the operator. This pausing is extremely, so it depends on the state backend, but it's very, very short because both the memory, like the heap-based state backend and also the RocksDB state backend, the only thing they do when the barrier is at the operator is that they create a copy of the hash map, but it's a lazy copy. So it's like a copy on write, copy on read data structure that creates a copy of the hash map lazily, and this way it will be able to perform a copy of the data without interrupting the live processing. And for RocksDB, it will also basically put a little marker into RocksDB, and then it will be able to read the data in the background and also perform the live updates on the stream. So the interruption is basically just acquiring a lock, so that the user function is basically done with the processing. It then sets this marker in RocksDB, or it creates it copies the data structure, and then it can continue with the processing.
It's the same with the file system DB?
Yes, so both the file system state backend and the RocksDB state backend support this in Flink. So the state backends are pluggable depending on the required performance characteristics and depending on the size of the state. So if your state fits into memory, of course it makes sense to keep it in memory, and then you will have very, very fast access to the state. But if your state is bigger than the memory, then you want to use RocksDB, where the state is kept in a temporary directory on files. And the RocksDB state backend also supports incremental checkpoints, which means it doesn't have to do a full copy of the entire state on each checkpoint.
So this network is actually asynchronous? This network is actually asynchronous? You said that there's kind of a very, very small pause. Then I guess the data is being transmitted to this distributed central store.
Exactly.
Which might take
Yes.
much longer time than the actual pause.
Yeah.
So it's kind of a limbo state in between where this network is not really available yet.
So the question was basically whether the checkpointing is asynchronous, and the answer is yes. And yes, also there is some in-between state, of course, but Flink, in case of an error, will always go back to the latest completed checkpoint. And also there's a configuration variable in Flink where you can configure how many checkpoints it has in flight at a time. So you can also control the behavior there. But it's extremely important to have the checkpointing asynchronous to the processing, because we're writing to a distributed file system somewhere. And if the service is not available, if Flink needs to retry, this also adds up to the time till the checkpoint is finished. So you want to have asynchronous checkpoints in basically almost all cases. Yeah. And I think it's a very powerful feature, because a lot of use cases are about low latency, and this asynchronous checkpointing allows you to achieve this low latency. Yeah?
Back pressure if the system is push or pull,
So the question.
Is too fast.
Yeah. So the question is about back pressure, and that's naturally handled by Flink. So there's no problem if in this topology, let's say this operator is slow, then it will not accept at some point any new network buffers, which means that these operators will not be able to send any network data. So these operators will also slow down, and it propagates till up to the sources. And this is not based on any heuristic, so it's by assuming this is some heuristic where they just slow down the processing. It's really just that it blocks on acquiring new empty network buffers. So it's a pretty powerful, simple mechanism. And the sources will just poll Kafka slower. So there's like a loop around the Kafka poll, and if Flink cannot send any data downstream, it will also not ask Kafka for any new data. And then of course your lag increases, but that's, I think, the most natural way of handling back pressure. And of course your latency goes up because you cannot process the data in real time, but there's a metric in Flink that shows you what the lag is. So I think it's manageable. And you can also rescale Flink, so you can also increase the parallelism so that Flink is using more resources in your cluster. And then it should, of course, process the data faster.
Auto-scaling is not automatic.
No, so Flink doesn't have auto-scaling. It supports rescaling through save points. So when you're taking a save point, which is just an addressable checkpoint basically, you can restore this save point using a higher parallelism. So we've talked about time already, event time and handling out of order events. And there's actually, if you think about it, there's very different notions of time. So starting from a Flink window operator. So you want to build windows where you collect data for 5 minutes. The easiest approach is that you're using processing time. So your operator sits there, looks at the clock, and waits till 5 seconds or 5 minutes are over, and then does the computation on the stream. The problem is that you cannot do, for example, any reprocessing. So if your Flink job was offline for 10 minutes, then the first window will contain a lot of elements. So reprocessing is not really possible. Also, the events will be congestion in the network will also cause the windows to be wrong, but the latency will of course be extremely low. The next time characteristic is ingestion time, which means that Flink assigns a timestamp as soon as the record enters the system. So in Flink, each record, so internally Flink has a field for each record where you can put a timestamp. It's just long, doesn't actually have to be time, it can just be a logical time. But Flink will automatically assign the time to each incoming record, and then you're at least not affected by any internal slowdowns by Flink. The next time is broker time. You can also ask Kafka to assign a timestamp as soon as the record is written into Kafka. And then Flink, so Flink's newer Kafka consumers are able to read the time, the event time that Kafka assigned to records, and then Flink's internal operators like the CP library, the complex event processing library, or the window operator in Flink will read this time. And the best time that you can get, the best time characteristic that you can get is event time, which means the source that generates the event is attaching the current timestamp to the record. So let's say you have an app, and whenever a user is performing an action, you're sending an event to your Kafka bus. And this app is just putting the current time at the mobile phone into the data stream. And then it doesn't matter to you if the user is, I don't know, in the subway and not available for 5 minutes because he's not connected to the data network. Or it doesn't matter if the user is at the airplane for 5 hours. Because as soon as the user is online again, all the events are streamed, and the window operator is just looking at the time when the event has been created, not at the time when the event has arrived in Flink. And that's extremely powerful, because with that, you can, for example, use Flink for batch processing. You can process data from 20 years ago, and the windows will still be correct. The data will still be assigned to the correct windows based on this time. It's a little bit like a second grouping or partitioning of your data. You don't partition it, you only partition it by the partitioning key, but you also basically partition it by time within the operator. And a very popular example that we use in our slides to explain this is Star Wars. Because the order at which you observe the events is not the order at which the events actually occurred in the Star Wars universe. And it also explains nicely the trade-offs that you do as an application developer. So, and Flink gives you the freedom to decide how you want to treat time. So I think the obvious approach for watching Star Wars, of course, is to watch it in event time. So you watch it according to the episodes, so that you have like the history in the sequence as they happen in Star Wars. But the problem is you're the uncool guy, because you first have to watch all the old Star Wars, so your latency is extremely high. And that's also the same consideration when you're implementing an application and you're processing event time. Your latency can be pretty high because you have to wait till all the out-of-order events have arrived at the system. So if you want to be the cool kid on the block, you just watch the Star Wars movies as they appeared in the movie theater. But of course you have very low latency because you can always watch the latest Star Wars movie, but it's harder for your brain to process the events. So I hope everybody understood now what event time is in Flink. So this is just a recap of everything with like all the core building blocks of Flink. And next I would like to look a little bit into the APIs of Flink, because the APIs of Flink allow you to use all these great features. And basically there are 4 abstraction levels in Flink to access these features. The main API that we've had for the most of the time of Flink is the data stream API. It provides you with sources like Kafka source, it provides you with map operations, with window operators, with co-map operators that have 2 inputs, like all the basic 7 minutes. 8 minutes, I'm sorry. Okay, so I have to hurry up. So basically all the basic building blocks for building a streaming application, but over time we actually found out that users want to access more the low-level features of Flink. They want to access the raw events, they want to access the raw state, and they want to access the time features. For example, this process function allows you to define a callback. So you can say to Flink, please call me again in 500 event time milliseconds, because I need to do something with my data. For example, if you want to have your data expire after a certain amount of time. That's when you use the process function. And also on top, we added streaming SQL and the table API for really doing high-level abstractions on top of streams. So let's quickly look a little bit at code. So that's the process function. Basically, you just have to read the comments. So this is how you access managed state in Flink. So as soon as you put anything in your application, like hash maps, counters, lists, whatever, it can also be the state of like an SBAR CP engine. As long as it's in this value state object, Flink will periodically serialize all your data whenever there's a checkpoint, and it will restore it for you with exactly what semantics. Then there's this process element function call, which is called every event that is coming. You're getting the actual event, you're getting the context, and you're getting an output collector for sending events downstream. Within the process element method, you see how to emit events, how to update the state, how to retrieve something from the state. And the thing I've mentioned, there's in the context a timer service that allows you to register a callback, which is very powerful for really building something custom. Like if you need to build a very fancy windowing function, that's the way to go. Because here you can define like a very custom trigger when you want to evaluate the content of your window, and the state of your window you would put into this state variable. And here, last but not least, is a callback for this timer. So here you can do all your stuff whenever this timer that you've registered is triggering. One level up is the data stream API. So that's the good old API. It has like a window operator for you. You don't need to worry about all the little details. It makes it quite easy to get started with Flink streaming. And also you can mix and match these APIs. So you can start with this API, but somewhere there's an operator where you're using the process function. Or you're using the SQL, the high-level SQL in Flink to do some data pre-processing, or you give it to your data scientist and then figure out the details and you just do the heavy lifting. So that's basically, it's a table API, it's like a DSL. For Scala in Java, we just support, you can just pass basically strings, we pass them and we translate them into an execution plan which is verified and then executed on Flink. Or you just give us an entire SQL string which also supports stuff like tumbling windows over with time, using event time. You can access the end of a window and you can do aggregations. So it's a pretty powerful API, and that's the reason why companies like Uber and Alibaba are using it, because it gives so many people access to these features. Alright, so I think we're running a bit low on time. So are there any questions?
I have a question.
Yeah?
Meaning the integration of Flink with things like Beam, Apache Beam, and everything.
Yeah.
And all the streaming processing thing there. And what are the things that you are doing as as the open source to be tackled that?
Okay, so the question is about the relationship between Flink and Apache Beam. So Apache Beam is a project that originates at Google. Google has this cloud data flow product in Google Cloud that is basically a pretty sophisticated stream processor, and actually Flink is following a lot of publications from Google, for example in the way we do event time that has been originally published by Google. And Flink is a runner in Apache Beam. So basically, if you don't want to pay Google for running your streaming jobs, you can also use the Google API, but execute it for free using open source Flink. And there's a lot of great things coming up in Flink through Beam. For example, Apache Beam is working on support for other languages than Java and Scala. So Flink is JVM-based framework, so you have to use Java, Scala, or anything that runs on the JVM. And through Beam, Flink will support Python and also more languages, as the Apache Beam projects and the Google folks are adding it to Beam. And there's also some activities around machine learning, I think, in Beam. So there's a lot of interesting things happening. Are there any? Yeah?
Is there any statistics? How do you create the execution platform given SQL? Do you collect some data? Do you collect some data? Statistics, distribution of the data? Runs?
Yeah, so Flink is using Apache Calcite for optimizing the SQL queries. It's the optimizer that is also used in Hive, Monet, and some other database systems. So basically, when you're writing a query, it will be translated into a calcite plan, and then it will be optimized and checked, and then translated either into a data set or data stream program. So you can use the SQL interface of Flink for both batch and stream processing, basically using the same syntax. And to answer your question, calcite has a cost-based optimizer, but I don't think that we provide calcite with any costs. I mean, the problem is also a little bit in streaming that, I mean, in batch, it's obvious. I mean, if you have a join and a small and a big data set, then you decide to use maybe a hash join and you know which is the build and the probe side. But for streaming, since data, you don't know how much data you're getting. So you could do some research into like iterative optimization or learning over time, but right now this optimizer is stupid. It's just doing like the standard optimizations like push down of filters, also this, what's it called, like selection push down into the data sources, but it's not doing sophisticated cost-based optimization. But I think in streaming there's also not a lot of potential. Yeah.
Thank you very much, Robert.
Thanks a lot. So very briefly, if you're interested to learn more about Flink, come to San Francisco in April or come to Berlin in September. These are all the companies that are attending and speaking. It's a really amazing conference. We also have training for Flink at this conference. It costs a little bit more, but it's not insanely expensive. And it's a pretty nice way of learning more about Flink. And if you want to come to Berlin, we are hiring as everybody, so talk to me. And also talk to me if you want to learn more about Flink. So thanks a lot.
Thank you.